Again, 913 surface integral. What's a surface integral? This is our topic today on this section. All right, to start with the surface integral, guys, let's suppose that you have a function y equal f of xy in a two-dimensional space. So this one represents always what? Represents a curve, right? So we have a curve that has beginning and it has an end. If I have a curve that has beginning and end, then definitely I can find what? The length of this. The length of this curve. Remember, we had it before. It's the square root of 1 plus dy over dx squared. Remember, if it's parameterized, we used to say what? Fx squared plus fy squared. But because the curve here is parameterized by y equal f of x, the derivative of x is 1, and the derivative of y is equal dy over dx squared. So this is actually the length of the curve in one-dimensional space. Now let's take z equal f of xy. Now I have what? I have a surface. I have a solid. What do we find? We don't find the length here. What do we find? We find the surface area. There are, in the previous ones, what did we find? We found what? The volume of the solid, right? In the previous sections, we focused on, especially in 910 and 911, we found the volume of a surface, okay, or a solid, where z represents the top, and we integrated double integral over r, and r can be type 1, type 2, or according to 911 is polar coordinate. So we were able to find the volume of the solid. What's the volume of the solid, if you remember? It's double integration of f of xy dA over what? R, where R is the base. This is something we did in 910 and 911. Now 913, we are trying to find now the surface area of this, of the solid, or of the surface. This is our solid or surface. I need to find the surface area. We can't say area. We say what? A surface area, because this is in three-dimensional space. The only difference here is that we're going to remove this and replace it with what? With the square root of 1, the derivative of x, and then plus the derivative of this with respect to x squared, and then the derivative of z with respect to y squared over a dA over the region R. So if I integrated what now? This is what? This is the length of any level curve in this one. So if we take the length of this, and it's just one of them, okay, and we integrate it over R, what do we get? We get the surface area. Right? This is the meaning of finding, this is a formula for finding the surface area. So what are we integrating? We are integrating actually the length, because this is the length of the curve. This is the length of the level curve in three-dimensional. So for example, if I have this sphere, suppose we have this sphere, guys, okay, and let's suppose that this is one of the curves, this one. This is the level curve, could be this one. The level curve could be this one, by the way. Anyone. If we take any level curve on this sphere and find the length of this level curve by using this formula, actually, which is square root of 1 plus fx squared plus fy squared. If we do this one and integrate it over the region R, what do we get? We get something called the surface area of that surface. All right, let's look at, like, for example, here's a surface here that you see here, three-dimensional surface. This is the top of it. This is z equal f of xy. This is our surface. What do we do to find the surface? We integrate over this region. This is our region, the base. We integrate over this. What do we integrate? The level curve, the length of the level curve. This is our level curve, for example. We find the length of this by using the formula, and then we integrate. Here's an example. Find the surface area of that portion of the plane. This is our plane that is bounded by the coordinate plane in the first octave. Okay, so let's take 2x plus 3y plus 4z. equal to 12. How do you graph this one? We know this is going to be a pyramid. If we let x equal y equal 0, then what do we get? 4z is equal to 12. This will give us that z is equal to 3. So that means when x is 0 and y is 0, z is a 3. If I take x is equal, z is equal to 0, then what do we have? We have 3y is equal to 12. So y is equal to 4. So 0, 4, 0 is the point on the y-axis. And this is what we call the y-intercept, actually. And this is the z-intercept. How about if we take y equals z equals 0, then what do we get? We get 2x equal to 12. So x is equal to 6. So we have 6, 0, 0 is the x-intercept. Now we will graph the question, the surface, actually. Here's the y-axis. On the y, it's 4. So 1, 2, 3, and 4. On the x, it's 6. 1, 2, 3, 4, 5, and 6. On the z-axis, it's a 3. 1, 2, and 3. So I have 3 points, guys, here. If we connect those with a straight line, and here with a straight line, and this one here. What do we have? He says in the first octant means what? Whenever z is positive, which is here, this is 3, as you know. Whenever y is positive, which is 4, and whenever x is positive, which is 6. So this will give us that. This is our surface. I need to find the surface area of this solid. What do we do according to the formula? We say that the surface area, AS, is equal to the double integration over our region R of the square root of 1 plus fx square plus fy square, then dA. Now we need to find fx and fy. How do I find this one? From here, 4z, I'm going to solve for 4z, is 12 minus 2x minus 3y. Divide by 4, so z is equal to 3 minus half x minus 3/4 z. This is z, by the way, and this is actually f of x and y. This is f of x and y. All right, now, what's the derivative with respect to x? The derivative of 3 is 0. The derivative of this x is minus half. And the derivative of z is 0. What's fy? My apologies, this is y. Okay. Now, what's the derivative with respect to y? It's negative 3/4. So what is this equal to? Double integral of the square root of 1 plus fx square is 1/4. This one is squared is 9/4. And this is, of course, dA over R, which is equal to, now, 1 plus 1/4 plus 9/4. This is 4 out of 4. So this is 14 out of 4. So this is equal to square root of 14 over 4 goes out. And I have double integration of dA over R. Now let's look at this R. Where is R, by the way? This is the region, right? This is the base of the solid. What is this? Let me graph it here. On the y-axis is 4, 1, 2, 3, 4. On the x-axis 6, 1, 2, 3, 4, 5, and 6. So what do we have here? We have a triangle of radius of, right triangle of base 6. Now, what is this? Remember, when there is nothing inside, what did I say? When there is nothing inside, so you are going to find the area of the region. This is my region, guys. This is, what's this? This is a triangle. What's the area of this one? It's half times the base, which is 6, times the height, which is 4. And this with this is 2. 2 times 6 is 12. So the answer is square root of 14 over 4 times 12, which is equal to square root of 14 divided by 2, because you can distribute the square root of 4 is 2, times 12, which is 6 square root of 14. This is, guys, the surface area of this surface. Got it? That's it. That's all you have to find. All right. Now, what did we get inside? Okay, dA. That's it. All right. Let's go to the second part. Find the surface area of the portion of this cylinder that is above the region in the first quadrant bounded by all of these. We have a cylinder, guys. This is our cylinder. We have x squared plus z squared is equal to 4. How does the graph look like? Let's see if the graph, we can really come to imagine how the graph looks like. All right. When you take here, if we let x equal to 0, so what do we get? We get z is equal plus minus 2. Here is 2. And down there, here is negative 2. When z is equal to 0, what do we get? We get x is equal plus minus 2. On the x-axis, here is 2. In the back, here is negative 2. So what do we have, guys? Remember, this is a circle of radius 2, isn't it? This one is a circle, but between x and z, here is z. So let me try to be accurate here. This is the circle of radius 2. Got it? So this is a circle, but in what? In the between x and z. But in this equation, we know that y is 3. So what should this circle do? It says cylinder. So this circle now is going to move along the y-axis in both directions, this way and in this way. Got it? So I have cylinders. In the first quadrant, who's going to come now? X equals 0. Remember, what's x equals 0? When I say x equal to 0, that means this is the YZ plane. Where is the YZ plane? YZ plane is exactly this plane. This is the y-axis. So what's going to happen here? We are going, you see, imagine this is like a tree, circular tree, right? This is a tree hanging here. What's going to happen is that we will have it cut in the back. So the back side is going to be cut. So the XY plane is going to remove this part. So it will be only what? This piece of it. Just that one. Sorry. It's just this one coming this way. All right. So let's change the color probably. Show you what I mean. It will be only that piece here. The back piece is going to go. Let's look at Z equals 0. When I say Z equals 0, what do you mean by? It's the XY plane. So what's going to happen, guys, now with the circle? The lower part is going to go away. So who's going to remain? So all of this is going to go away, with all of this is going to go away. Nothing at the bottom. So we're going to be left with just that part. So I'm going to change this color to green probably. So when the bottom one goes away, you're left with this part. Y equals 0. It's the XZ plane, which is exactly this one, guys. XZ plane. So what's going to happen? That thing is going to go away. So I'm going to erase these left points. So we don't need this and we don't need that. So everything in the back is going to go. So all I have now so far is just this green. And then what's going to happen here? We have y equals 0. We did this. Y equal to 5. Where was y equal to 5? Let's suppose this is 1, 2, 3, 4, 5. What's going to happen here? Y equal to 5. It's this plane, guys. Y equal to 5. It's exactly the plane that is parallel to this plane. These two planes are parallel. So to be more precise, let's erase this one and let's erase. Okay, let's make that nicely. All right, so here you can come like this, like that. And then this goes down here and down there. And this is what 5. So this is going to cut the circle or that tree here. So what's the result of the cut? It's exactly this. But what did we say? We don't want this. So I'm going to remove that. We don't need the back one. And from this one, I need only, so I'm going to make the black one. So let's go to make the coordinates here. This is again the Z axis. And here is the parallel to the X axis. And this is the Y axis. So what's going to happen? So this is going to come here. Here it is. And here it is. So what do we have at the end? I just need this, 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 and that. And then this goes down here. And we have this is the piece. So we are left with this like a goalie thing. Let me graph it here. That part goes down. And then at y equal to 5, we make the x-axis, z-axis, and we make the same graph here. Then we connect that, connect up there. And this is the final shape, guys, of our region. Why is that? You see, it was a full tree. We cut it from the back. We cut it from the left side. Here, it was cut here. Where am I? Yeah, it was cut from here. It was cut from the back. It was cut from the bottom, right? From the bottom. And it was cut from here, right? At this y equal to 5. So what's left from the whole tree? Just a quarter of it that is in the XYZ plane, all in positive, in the first quadrant, or what we call in the first octant. So this is, guys, our region. We know that this is 2, and this is the base of our region. And this is the top. Who's this? This is Z equal, guess what? We have Z square equal to, so we know from this one, Z square is equal to 4 minus X square. So that means Z is equal plus minus square root of 4 minus X square. The positive part is the top one. So this is the square root of 4 minus X square. The bottom one here is Z equal minus 4 minus, but we don't want it. We already cut it. So this is, guys, our surface here. You notice here that this is our surface. This is the shape that we're talking about. So the top part is Z equal 4 minus, because it's part of that circle, isn't it? Done. So what do we do now? We need to find the surface area. What's the surface area equal to? The surface area is equal to the double integration square root of 1 plus fx square plus fy square, then dA over r. All right. Now what's Z we said? Z here is equal to square root of 4 minus x squared. That's Z. We're going to differentiate, and this is, of course, what? This is f of xy. What's the derivative of this with respect to x, guys? You know, this can also be written as 4 minus x squared to the power half. Let's differentiate this. What do you get? Half goes down. Then 4 minus x squared, reduce this by 1, becomes my negative half, times the derivative of the inside, which is negative 2x with respect to x. This 2 goes with this 2. So, and you're left on the top, you have minus x over, you see this negative power, I'm going to bring it down, becomes what? 4 minus x squared at the bottom. This is fx. How about fy? There is no y whatsoever for f. So that's a 0. So what is this equal to? Square root of double integral, square root of 1 plus square this one now, right? It's fx squared. When you square that, what do you get? You get x squared over 4 minus x squared dA over r. Let's simplify this one more. So this is equal to double integration of square root of, this is 1 over 1. So multiply, let's make the same denominator, 4 minus x squared as the least denominator. So this is going to be 4 minus x squared plus x squared dA over r. And this goes with that. Square root of 4 is 2. So it's going to do double integration of 1 over square root of 4 minus x squared dA over r. This is the leftover. All right, so this is our final derivative. All right, how do you do this one? If we divide it by 4, actually, I don't know if you remember this one. What's the integration of a squared minus x squared? So before we do this one, let's go first to the limits of integration. Where is r? R is this region, guys. So this region, if I graph it here, x is 2 and y is 5. That's the region. It's a rectangle. You can take it region of type 1. So that means on the x-axis, so this is equal to the double integration of 1 over square root of 4 minus x squared. And now I'm going to make this one dy dx, region of type 1. So we're going to go from where? This is going to cover the whole region, you're going to start from 0 to 2 on the x-axis, right? From 0 to 2 on x. How about on y? Well, who's the bottom one? This is y equals 0. By the way, this is x equal 2. And this one, x equal 1. So that the scanner is going to start from 0 to 2. On the y-axis, from 0 up to here. What is this? This is y equal to 5. So on the y, it's from 0 to 5. This is finally the final form of the surface integral. Now what do? We start the integration from inside. Don't forget we are integrating with respect to y. So this is all constant. So what's the answer here? Integration from 0 to 2. Open the box again. We only integrate dy, which is y. So y over 4 minus x squared. And this is from 0 to 5. dx. Put the 5. So this is the integration from 0 to 2 of 5 divided by the square root of 4 minus x squared dx. I will take this one to the next page, the integration. So this is equal to the integration from 0 to 5, 0 to 2 of, go back, what's on the top? 5 goes out. Let's make the 5 out. 1 over square root of 4 minus x squared dx. I think there is a formula which says that the integration of such functions are equal to So you could do this one by using what you call it, integration by trig substitution, or you can use formulas that are ready for such integrals. All right, so I'm going to use the textbook here where I'm looking at the integration of, let me see if we can find it. Yeah, here it is. Just 1 second. Yeah. So there's a formula which says that the integration of dx over the square root of a square minus x square is equal to, this one is equal to sine inverse x over a. All right, this is a formula for such integral. So I'm going to use that integral, which is in the book, and say this is equal to 5 sine inverse of x over, what's a here? A is 2. And this is from 0 to 2, guys. You see, straightforward if we know this formula. And this is equal to 5 sine inverse. If I put 2 first, we get 1 minus 5 sine inverse 0. Sine inverse 0 is a 0. Sine inverse 1, what is the theta that gives me 1? It's pi over 2. So this is 5 times pi over 2. So it's 5 pi over 2. This is the final answer. All right, let's look at this question. Find the surface area of the portion of the paraboloid z equal x squared plus y that is below the plane z equal to 2. So let's find how the graph looks like. All right, so the first thing we're going to take now is z equal x squared plus y squared. Go back, guys, to the previous graphs. We know that the graph looks like this. It's a paraboloid that is open upwards, right? It is our paraboloid that is open upwards, okay? And then who's going to come? Z equal to 2. Z equal to 2. What is this? This is, you go to 2 here, and what do you make? You make a plane. I will erase it in a minute. Here is a plane. I'm going to make it actually somehow with fade color. This is, guys, the plane z equal to 2. It will cut it like that. What's the result of the cut? The result is going to be this circle. So z equal is going to come and everything is going to go away. So we are left only with this one. So this is our circle at z equal to 2. What is this circle, by the way? Put it 2 here. If I take these two equations, so what do we get? So you get x squared plus y squared equal to what? Equal to 2. So this is the result of this one. So this one is x squared plus y squared equal to 2. What is this? This is a circle of radius what? Square root of 2, right? So the radius here is the square root of 2. So if we go back down here now, so look what's going to happen. If I bring this circle down, what do we get? We get on the xy plane, we get a circle of radius root 2 on the y-axis, and this is root 2 here, and it's root 2 on the x-axis. So this is the projection of it. See, because every solid must have a projection on the xy plane. Now, what does he want to find? He wants to find the surface area. The surface area is equal to the double integration of square root of 1 plus fx square plus fy square dA over r. All right, now, where is f? We know that z is equal to x squared plus y squared. So this is actually our f of xy. Let's differentiate it partially with respect to x. What do we get? We get 2x. And the partial derivative with respect to y is 2y. So this implies that the square root of this is 1 plus, if I square this one, I get 4x squared, and you square the other one is 4y squared, and you can write this one as 1 plus 4x squared plus y squared. I can take the 4 out. Nice. So what do we have? So now, so the area, surface area, is the double integration of the square root of 1 plus 4x squared plus y squared dA over r. Now the question, where is r? To see where r is, this is our base. If you flip that solid, flip it, so it will stand at this one. So I'm going to graph it here. Exactly what do we have on the xy plane? We have a circle of radius root 2, isn't it? This is all root 2. Because it's circular, so what do we do, guys? We are going to solve it by using polar, isn't it? The best thing is to do polar. So what is this equal to? Double integration of the square root of 1 plus 4r squared. And then what do we say? R dr. D theta, remember in the polar, this is r squared. And then r is the length. We start from where? 0 up to root 2. So r is from 0 to root 2. Okay, to cover the whole circle, how much I should rotate? We should rotate what? 0 to 2 pi. That's it. This is the result of the integration. Now, how do you integrate this one? Let u, I'm going to do it here, let u equal to 1 plus 4r squared. So du over dr is equal to 8r. Bring dr here. So du is 8r dr. I have r dr. Remember, we always integrate from inside first. So divide by 8. So du over 8 is equal to r dr. All right. So this is equal now. Integration from 0 to 2 pi. Then open the box. It's the integration from 0 to square root of 2 of what? I called this one u. So it's going to be the square root of u. And r dr is du over 8. So du over 8 d theta. And this is equal to integration from 0 to 2 pi. Now, the integration of root 2 is u to the 3/2 over 3/2 times what? Times 2 over 3. And don't forget there is an 8 at the bottom. The integration of u to the half, you increase the power by 1. So 3/2 divided by 3/2 means multiplied by 2, 3. And this is from 0 to square root of 2. D theta. Now, what's u? U is 1 plus 4r squared. So, and by the way, this one with this one is 4. 4 times 3 is 12. You can take it out. So we're left with the integration of 0 to 2 pi of 1 plus 4r squared to the power 3 over 2 from 0 to root 2 d theta. What do we plug first? Root 2. So this is equal to 1 over 12 integration from 0 to 2 pi. Now, so it's going to be 1 plus, first we're going to replace 3/2 here. Sorry, square root here. Square root, when you square it, you get 2 times 4 is 8. to the 3/2 minus, what do we put now? The 0. If I put the 0 here, you get 1 to the 3/2 d theta. This is 9. 9 to the 3/2 is 3 square to the 3/2. 2 goes with 2, and you have 3 cubed, which is what? 27. So all of this is 27, guys. Minus 1 is what? Is 26. So this is going to be 26 goes out of 12. Integration from 0 to 2 pi d theta. And this is equal to, this is divisible by 2, you get 6. This is divisible by 2, you get 13. So you have 13 over 6. The integration of all of that is 2 pi. Now this one with this one is a 3. So the answer is 13 pi over 3. And this is actually the surface area of this solid. Let's look at this one. Find the surface area of those portions of the sphere and within this cone. Oops. Okay, let's see what we have here. Let's graph it. All right, the first one is the sphere of radius √2, right? This is sphere radius √2. So let's suppose that this is √2, guys. So in the back, minus √2. Here you have √2. At the bottom, of course, you have minus √2. And now we can graph the sphere. So I hope I can make a good graph here. And then we go all the way up. And you know, on the x-axis is going to be here, √2. So we're going to go all the way down to √2. And in the back, you can put the divided 1. And here, you go to √2 again in the front. And in the back, you go to minus √2. And you make your sphere. So I have sphere of radius √2. The second one, he says this is a cone. I showed you before that this is a cone. So what do we have? Let me graph the cone in different color now. This is our cone. It has the upper one, and there is a one at the bottom. Okay. We make better. And then it will be like this. So we have a cone and a sphere. So it's going to be between those, within those, right? So where's my region? So this is exactly what I'm talking about, actually. Finally, here's one piece. So I have this cone, you see, and that's the top of it. So it's covered on the top by this what? This sphere. So this one is z equal to 2 minus x squared minus square under the square root, isn't it? This is the top one. The bottom one here is z equal minus 2 minus x squared minus y squared. So this is actually our f. So z here, which is f of xy, the top is going to be square root of 2 minus x squared minus y squared, of course, plus and minus. Now what I'm going to do, I'm not going to bother myself with the bottom one. So I'm going to find the surface area of the top one and multiply the whole thing by 2. So what do we say here? We're going to say here that, so this is actually the positive part. So fx is what? By the way, this is equal to this, to 2 minus x squared minus y squared to the power half. If I need to differentiate this with respect to x, the power goes down. Then you have 2 minus x squared minus y squared to the power half minus 1 is minus half, times the derivative of the inside with respect to x, guys, which is minus 2x. This 2 now goes with this 2. I am left with minus x divided by, this one goes 2, so this is 2 minus x squared minus y squared. This is fx. Similarly, by the way, fy will be what? Minus y over square root of 2 minus x squared minus y squared. This is fy. Remember, in the surface area, I have to do 1 plus fx squared plus fy squared, isn't it? So this is the square root of 1 plus, if you square the first one, you get x squared over 2 minus x squared minus y squared, plus, if you square this, which is that one actually, you get y squared over 2 minus x squared minus y squared. Let's simplify this one further. So this is 1 over 1. So the least common I'm going to take is 2 minus x squared minus y squared. So this one becomes what? 2 minus x squared minus y squared. Then plus this x squared here plus y squared. Minus x squared goes with plus, minus goes with plus. I'm left what? On the top, what do I have? Square root of 2. At the bottom, square root of 2 minus, I'm going to factor out the minus. So what is this, guys? This is the inside of the surface area. What's the surface area equal to? It's double integration of the square root of 1 plus fx squared plus fy squared, then dA over r. And this, we found it. Here it is. So this is the double integration of 2 over square root of 1. Is it 1 or 2? It's 2. Now all of this is 2, sorry. Okay, so this is 2 minus this one. I'm going to write it as r squared. And I'm going to say r dr d theta. Why is that? Look at what is the result. If I flip this one, guys, here's our circular. So this is the result of the intersection between the cone and what? And the sphere. So what do we have here in the sphere? I have this. I have x squared plus y squared plus z squared is equal to 2. The cone is x squared plus y squared is equal to what? Z squared. So what I'm going to do, I'm going to replace this one with what? With z squared. So we have z squared plus z squared is equal to 2. So 2z squared equal to 2. So z squared is equal to 1, which implies that z is plus minus 1. So this one on the z-axis, guys, is 1. Here it is. And here is minus 1. See, the minus 1 comes here. And don't forget to multiply it by 2, because I'm not going to deal with the bottom one. I'm just going to find the top one. Okay, when z is 1, can you tell me what's this on the y-axis? We know here, you know, this one is y equal z. So if z is 1, so what's this one? It's a 1 here. Also here, you get negative 1. So the base now is this one. This is our base, not the sphere, just that part. So our graph actually, if we do this one in green color, here it is. Okay, that's the base of our region of the shape, because if you flip that cone, it will sit on that circle. It's a circle of radius 1. All right, because it's a circle of radius 1, let me take it here. And let's say this is our R. Starts from 0 to what? To 1. So R is from 0 to 1. And to finish the whole circle, to rotate on the circle, you know, you have to go from 0 to full rotation up to 2 pi. That's it. We just set up the equation. How do we integrate this one? Remember, we go inside. We go inside. So I will take you to the next page. So we have, let me change the color because the green is too light here. Let's take this one. So we have integration of, right, it's the integration from 0 to 2, integration from 0 to 1 of 2r on the top over square root of 2 minus r square dr and then d theta, and we are dealing with the inner one. Let's see what we have. Oh, yes, this is what we have exactly. Now, how do you integrate this one, guys? So I need to integrate 2r over 2 minus r squared dr. How do we do that? Let u 2 minus r squared, the inside. So what's du over dr equal to? It's negative 2r, isn't it? Bring this one here. So du is minus 2r dr. But I have 2r dr. So minus du is 2r dr. So what is this going to be, guys? It's going to be all of the top is minus du over this one. I called it u, so this is square root. You can take the minus out, and you're left with u to what power? Negative half du, right? Because you bring it up. What's the integration of that? You increase the power by 1, becomes u to the half, divided by half, which is times 2. So this is the answer. So it's minus 2, but what's u? U is 2 minus r squared to the power of half, which is equal to minus 2 square root of 2 minus r squared. So this is equal to the integration from 0 to 2 of negative 2 square root of 2 minus r squared. This is from 0 to 1 d theta. Now let's plug the one for r, guys. So what is this going to be? The integration from 0 to 2. Negative 2 square root. If I put 1 here, 2 minus 1 is 1. Minus and minus becomes 2 square root. Put the 0, you get 2. All of this d theta. So minus 2, this is 1. So this is minus 2 plus 2 root 2. All of this goes out. I'm left with the integration from 0. Sorry, where's the other one? D theta from 0 to 2 pi. We'll go pi here. Pi. 2 pi of d theta. And we know that this is 2 pi. So with this one is going to be what? 2 pi, then minus 2 plus 2 root 2. This is the answer of that one. All right, now let's talk about the surface integral. What's new now? It's our topic today, by the way. Let's look at the function g, by the way. This g is a function of x, y, and z. When you have a function of 3 variables, so it's w equal to all of that. So we know that the graph of this one is going to be over what? Over 4-dimensional space. We don't know how to do that. But when you if you want to integrate this function, then you have to integrate it over a surface. Remember, when it's a function of x and y, you integrate it over a region, right? Remember, if I want to integrate just f of x, we say dx from a to b. So integrate it over a line. If I have f of xy, what do I integrate it over? Over a curve, right? But if I have f of xyz, also I can integrate this one what? Over double integral f of xy dA over a region, isn't it? Region in where? This is in 2-dimensional space. 2-dimensional space. But if I have f of x, y, z, I want to integrate this one. What do I integrate this one over? Over a surface. In what? three-dimensional space, because this is the three-dimensional. Clear? All right, and this is what we have, and we say what? Over the surface. So a function of three variables must be integrated over a surface. But this is difficult to integrate. So what do? We know that ds is equal to that, right? Remember in the previous one, the surface area, what's inside? This is what's inside the surface area, isn't it? And this is the surface area, and then we integrate it over R. That's period. This is what we do. And if z is if we're gonna replace x with f of xy, z f of x, which is usually all our questions like that. So what do we say in this case? We will differentiate respect to x and y, and we square it. If we are dealing with g as a function of x and z, then we say gx and gz square. If we are talking about x as a function of y and z, then we say hy square and hz square. And this is how you integrate this surface integral. So what's the surface integral, guys, in general? This is the major theorem. This is the major one. This is what I'm talking about. This is called the surface integral. We are integrating a function of four variables over what? Has to be over a function of three variables. Over what? Over a surface. And to do that, we replace ds with the surface area, and we integrate over the region. See, if I remove this, what do we have? Surface area. If I keep this, what do we have? I have no idea yet. I'm going to show you in a minute, but we're going to keep that. So now, so this is the idea now again, guys. So what do we have? We are integrating a function of three variables. Function of three variables. What do I integrate it over? It has to be integrated over a surface. Okay, what's the surface area? This is the surface area over the region R. So it's the same previous one. It's a surface area, but when I put another function inside, it's not a surface area anymore. What is this called? I have no idea yet. I'm going to show you in a minute. All right. So let's look at this one. Evaluate this surface integral, where g is given to be x, and s is the surface of this in the first octant bounded by all of those. So let's graph our surface, guys. I am integrating over a surface. So what does the surface look like? Let's see it. All right. When I say y equal to 0, remember, y equals 0 is what? This is the xz plane. Here it is. When I say z equal to 4, you're going to go to 4 here. 1, 2, 3, and 4. And you make what? Here. Let's make the same like this, xyz plane. And we take this plane. All right, that goes back also. So the result is another plane parallel to this plane. All right, this is the result. Now, we have this guy. What is this? Z equal 2 minus x squared. Remember, this is, if I let z equal to 0, so what do we have? We have x squared equal to 2, isn't it? So x is equal plus minus 2. So a square root of 2, of course. Let's suppose that here is a square root of 2, and in the back, this is minus square root of 2. What am I going to graph? You see, this one is parabola open downwards, but it's shifted 2 units up on the z-axis. So this is the graph of our parabola. This is actually our graph. I'm trying to be better in graphing. So let me make it neat. See that? It's like this door here. But we have also x equal to 0. What's x equal to 0? This is the YZ plane. So here's the YZ plane. What is this going to come? It's going to cut that part. So who's left? Just this part. Also, y equal to 0, it will cut. So this is supposed to move in this direction and in this direction. Again, it's going to move also in this direction. But what's going to happen here? We are going to be facing this plane who is going to cut it also at 4. So there will be a cut also here. And this is our final shape, guys. So here it is. So we just need that part. Okay, just the front one. So this part here goes on the top, then this one. So let me maybe change it in colors red so you will see it. So it's this curve. That is moved here. See, in the back, it's cut. And I have this front here. Okay. It's only the top one here. And that's the only thing that is left. It's that red one. Who's that here on the top? See, this is our shape. Right? It's like nice box like that. It's cut from the back. Z equal to 0 is what? Is the XY plane. So you see this curve is supposed to go down, continue, but I'm going to cut it with what? With Z equal to 0. So we got it from the bottom. We're going to cut it here at what? Y equal 4. What is this? This is Y equal 0, the cut. Who's this in the back? This one is X equal to 0. So all of those cuts are going to lead with this graph only. What do we need to do now? We need to integrate this one. So what do we say? Okay, he wants to find the integration of G of X, Y, Z over S and S. What do we say? This is double integration. G is given to be what? X. Now we say ds over S. But what does the formula say? This is equal to the double integration of x times the square root of 1 plus fx square plus fy square dA over r. So now let's find the missing parts in this formula. Okay, here is fx. We know that here is z. We know that z, which is actually f of x and y, is 2 minus x squared. So what's fx, guys? What's the partial derivative with respect to x? It's minus 2x. Fy is 0. There is no y to differentiate. So that means the square root of 1 plus fx square and fy square is the square root of 1 plus fx is the square root. You get 4x squared and fy is 0. So this is what's left. So what's my question going to be now? It's double integration of x times the square root of 1 plus 4x squared. Then what? dA over r. Where is r, by the way? This is our region r. This is the base, isn't it? Let me take it here. On the y, it's 4. On the y, it's 4. This is the y-axis. On x is only root 2. So what do we, we have this rectangle. So this is our region R. Look, because the derivative of this is 8x, which is available. So I'm going to integrate with respect to x first, then y. And what is this? This is a region of type 2. Remember, when you make it dx dy, you make it a region of type 2. So your sector is going to be horizontal light, horizontal sector. Starts where? On the y. This one is y equals 0. And this one is y equal to 4. So with y, 0 to 4. But for x, this is what? X equals 0, and this is x equal root 2. So it's from 0 to root 2. Now what do? We integrate from the inside. So we start with inside. Alrighty. How do you integrate this one, by the way? You let u again equal 1 plus 4x squared. So du is 8x dx. In the question, what do I have? I have x dx. Divide by 8, so du over 8 is equal to x dx. That means the integration of x times the square root of 1 plus 4x squared dx is equal to, I call this one u, so this is u to the half or square root of u. X dx is du over 8. Take the 1/8 out. What's the integration of u to the half? It's u to the 3/2. You increase it times 2/3. This 2 with 8 is 4. And we are left with u to the 3/2 over 4 times the 3 is 12. But u is 1 plus 4x squared, so this is 1 plus 4x squared to the power 3/2 divided by 12. This is the result. So this one equal to the integration from 0 to 4. Open the box, 1 plus 4x squared to the power 3/2 divided by 12 dy, and this is from 0 to square root of 2. All right, now, what do, guys? We replace square root 2 for x. What do we get? We get 4. Square root of root 2 is 2 times 4 is 8 plus 1 is 9. So this is equal to the integration from 0 to 4 of the following. When I put here, we said this is 9 to the 3/2. So this is 9 to the 3/2 over 12 minus, if I put the 0 now here, what do we get? 0 plus 1 is 1, so it's 1 over 12. And dy. But this one is a 3 square, which is, square goes with square, and you have, so this is 27 over 12. So this is equal to integration from 0 to 4 of 27 over 12 minus 1 over 12 dy. And this is 26 over 12. Goes out, integration from 0 to y of dy. And what is this equal to? 26 over 12. What's the integration of dy? It's y from 0 to 4. Put the 4, you get 4. So the answer is 26 over 12 times 4. This one with this one is a 3. So you have 26 divided by 3. This is the answer for this surface integral. Now let's talk about orientation of a surface. Surface orientation. Sometimes we have something called orientable surface. What do you mean orientable surface? Means, look at this red box. From outside is red. I can easily paint the inside with what? With blue. Look at this football. From the outside, it's black and white, but for inside, I can make it yellow. So if you can paint the outside with a color completely different from the inside, then this is called orientable surface. So if I take the inside out, it's going to be completely different surface, isn't it? Face. There are some surfaces that are not orientable. You know, like this is called the Mobius here. Look at this one. What do I mean by not orientable? So follow me here with the red line. Let's start with here, guys. I'm here now. I'm gonna move. Move. So now I'm outside. You see that one? I am out. Keep on out. Keep on out. Now, what am I gonna, I'm still out, right? So this is going out. But look what happened after that. I'm not gonna be here, I'm gonna go in. So I was out, but with this flip, twist, I got in. So the in and the out are the same. So this is not orientable. Try to flip it, bring any, elastic thing, cut it, flip it, join it again. You find that you can always see the out is in and the in is out. So this is not orientable. In this section, we are going to deal with orientable surfaces only, where the out is out and the in is in. Like this surface, this sphere, for example, or Earth we're living in. There's the outside where we live in, and there's the inside, which is inside. Now, sometimes things go outside the surface. If the thing goes from inside to outside, it's called upward oriented surface. Upward orientation. If you go from inside out, and it's downward orientation if things are going inside the object. So if things are going inside the object, when you are inflating like a football, that's downward orientation. When things goes out, when the air goes out of this, it's outside, out there. A good example is the sun. Since these rays, all those rays are what? Are upward oriented because they're going outside the sun. Clear? So this is a nice upward and downward orientation. All right, now. If a smooth surface is defined by this, I have a surface. I'm going to show you how is this one. How do we get this one? Remember, the surface is not like this, isn't it? The surface is never like this. How is the surface defined? The surface is defined like this. Z equal f of xy, isn't it? Right? Yeah. If I move this to the other side, see, it's going to be minus, huh? So what do we have here? How many variables we have? X, Y, and Z. So Z minus f of xy, I'm going to call it g of x, y, z. This function is equal to what? When I move everything to the left, what is this supposed to be equal to? 0, isn't it? When you move this to this side, what's left on the right? 0. So Z minus f of xy is what? Is 0. What do we have here? Function of 3 variables. So I'm going to call this one g of x, y, and z equal to 0. So now the left-hand side is 0. Now, this function is outward oriented if you make it z minus f of xy. If I move z here and I say f of xy minus z equal to 0, this is inward orientation. So z minus f of xy is outward orientation. F of xy minus z is inward orientation, and this function will be oriented outward, and this is oriented downward. And you have to be careful. Inward and outward, downward or outward, it's the same thing. All right. So you will be given the surface. The question will not give you this. You will be given a surface equation. Move f to z, you get g equal to 0. So this is our g function now. All of this is our g if it's oriented outwards. I'm going to call this one g. What I'm going to find? I'm going to find something called the n. You know what's n? Let me go to the graph. This is n, by the way. Here is n. It's a vector that oriented upwards. Okay, and this is a unit vector. Why? It's, remember the gradient of the function. Remember, what's a gradient? Isn't it the vector that is perpendicular to the surface? Remember that? So this is exactly. So the ray that comes from the sun is the vector that's what? Perpendicular to the sun. But it goes all the way. If I need to make it a unit vector, what do? We divide it by its gradient. And remember, what's a gradient of a function in 3-dimensional? It's the partial derivative with respect to x, with respect to y, with respect to k. And this is the gradient. Divide the gradient by its magnitude, you will get a vector called n. What's this vector n? It's the unit vector that is oriented either outward or inward, depends on G, and it is perpendicular to the surface. Here's an example. Consider this sphere. All right? I shouldn't say maybe sphere. It looks like it, but yeah. Suppose this is the equation of a positive radius A. Find the upward and downward orientation of the n and minus n. Okay. Now we have n is what? It's the gradient of G over what? Over the magnitude of the gradient of G. Now what's G? The question. Look what we have here, guys. We have Z equal to 4 minus x squared plus y squared. I'm going to move everything to the left. By the way, this one is f of xy. Move it to the left. What do you get? You get z minus 4 plus x squared minus y squared is equal to what? 0. What do we call this one? This is g of x, y, z, which is z minus 4 plus x squared minus y squared, and this is oriented upward. Why? What did I do? I said z minus f of x. All right. Now, what's the gradient of g? It's the partial derivative of g with respect to x, guys. What's the derivative of this with respect to x? Here's the only place where you have x. So it's 2x I. Then plus the derivative of this with respect to y, partial derivative. What's the derivative of that? Minus, so it's minus 2yj. Plus the partial derivative with respect to z, the derivative of z is 1. So, okay, this is the gradient of g, guys. What's the magnitude of the gradient of g? It is the square root of the square of the first, which is 4x squared, plus the square of the second, which is 4y squared, plus the square of the last, which is 1. So what is n now? It's the gradient of g, which is 2xi minus 2yj plus k divided by the square root of 4x squared plus 4y squared plus 1. This is a vector that is perpendicular to the surface and it's oriented upwards. Clear? We have this before, but it's in a different way today. All right, consider this sphere now. How about this one? Same thing. But by the way, we didn't do the negative one. So this is then upwards. Inwards, what's going to be n? This is minus 2xi plus 2yj minus k divided by square root of 4x squared plus 4y squared plus 1. This is the vector that is perpendicular to the surface, but it's what? Inward. Oriented inward. Same idea here. Look here, I have x squared plus y squared plus z squared equal a squared. Move everything to one side. X squared plus y squared plus z squared minus a squared is equal to 0. Now, this is considered, this is the g of x, y, z. Now, what's the gradient of g? It's the partial derivative with respect to x, which is 2xi. The partial derivative with respect to y is 2yj. The partial derivative with respect to z is 2zk. The gradient of that is the square root of 4x squared plus 4y squared plus 4z squared. N here is going to be 2xi plus 2yj plus 2zk divided by square root of 4x squared plus 4y squared plus 4z squared. Minus n is minus 2xi plus 2yj plus 2zk divided by the square root of 4x squared plus 4y squared plus 4z squared. This is the inward vector, and this is the outward vector, right? Oriented outward, and this is the vector oriented inward. Those are the perpendicular vectors to the surface. And this will take us to the last part of this section, guys, which is called the flux. When you open the faucet in your house, the water comes out of it, huh? So we are going to measure the flux. The volume of the water that comes out of there is called the flux. We will be able to measure that flux. To measure the flux, I must give you the velocity field. Remember, we are in three-dimensional space. So first, I'm going to give you the velocity field, the force that pushed the water out. It's a vector force, isn't it? That's one thing. Who's going to also, in order for the water to get out of the surface, what do we need? We need a vector that push this force what? Out. Which vector is that? The perpendicular vector to the surface, which is what? N. And we will take F dot N, and we will integrate this one over what? Over the surface. So you have a surface, okay? And this is called, by the way, this is called what? Surface integral, because I have to integrate a surface. You see, this is g of xy. Remember in the previous, I just talked about the surface integral. Now, if I integrated the surface with F dot N, what's F dot N? It's the force that is pushing the water out if N is oriented outwards. If N is oriented inward, this will give me the flux of water that is coming in. Clear? If N is going outward, and you know this is N, this will give me the volume of the water that is going outside the surface, and it's called the flux, outward flux. If N is inward, so it's inward flux. This is the formula for finding the flux, guys. I will conclude the section with these two examples. Let's suppose that F represent the flow of the fluid, which means what? The velocity force. Find the flux through the surface S given by the portion of this plane. Okay, we have this plane, guys. We have Z is equal 6 minus 3x minus 2y. The first thing I would do, guys, is I would put the formula. Flux is equal to the double integral over the surface S of F dot N, then ds. So far, so good. This is what we have. But remember, in the surface integral, we can't integrate over S. So what do we say? So this is F dot N. This is going to be changed to what? Remember, 1 plus fx squared plus fy squared. Then we say dA over what? Over R. Remember, this is the formula, actually. This is the flux formula. So if you go back here, here it is. ds is equal to all of that. Now it's becoming easy to find. The first thing I would do is to think of n. What's n? Gradient of g over the magnitude of a gradient of g. Find the flux through the surface, okay? Given this, let's suppose it's pushed outside, oriented outside, outward. Goes outward, outside. All right, so what do we do here? Look at this. We have Z is equal to 6 minus 3x minus 2y. This one, by the way, is f of x and y. So this implies that z minus 6 plus 3x plus 2y equal to what? 0. I moved everything to z. What is this, by the way? This is z minus f of xy because it's oriented what? Outwards. So this implies that g of x, y, and z, all of this on the left. So it's z minus 6 plus 3x plus 2y. That's g. What's the gradient of g? It's the partial derivative of this with respect to x, which is a 3i, plus the partial derivative of this with respect to y. The derivative of 2y is 2j, plus the partial derivative with respect to z, which is 1k. The gradient of g, magnitude, is a square root of 9 plus 4 plus 1, and this is a square root of 14. So what's n now, guys? It's the factor that is 3i plus 2j plus 1k divided by square root of 14. That's n. All right, now, what do we need? We need f dot n. F dot n. What's f in the question? Here it is. F, by the way, is 0i plus zj plus zk. I want to multiply this by this n, which is 3i plus 2j plus 1k divided by square root of 14. How do you multiply? Remember, the first by the first. 0 times is gone. Now z times 2 is 2z plus z times 1 is z divided by square root of 14, which is a 3z over square root of 14. This is f dot n now. Now who's left? This part. How do you find this one? Now in the question, z is our f of x and y is 6 minus 3x minus 2y. So what's fx, guys? Partial derivative with respect to x, it's negative 3. What's the partial derivative with respect to y? Is minus 2. So the square root of this, it's 1 plus 9 plus 4, which is going to be square root of 14. By the way, this must match this. They must be the same. So let's go to my question. So flux, what is it equal to? Double integration. F dot n, what did we get? Where is f dot n? Here is f dot n. So it's a 3z divided by square root of 14 times this all is a square root of 14, right? This is a square root of 14, dA over this one goes with that one. The 3 goes outside, so you have 3 double integration of z. But what's z in the question? It's 6 minus 3x minus 2y dA over r. All right, guys, so this is the formula. Now the question is, what on earth is my region? Where is my surface? This is my surface. Remember, always the surface in the z equation. So let's think of this as a surface. You have z. Move everything to one side. So you have 3x plus 2y plus z is equal to 6. Now, do you know how to graph this one? Let x equal y equal 0. So what do we get? We get z is equal to what? 6. So we have here x is 0, y is 0, z is 6. Let x equal z equal 0. So what do we have? We have 2y equals 6. So y is equal to 3. So the second point is 0, 3, and 0. Now let y equal z equal 0. So that means 3x equals 6. So x is equal to 2. And here we have 2, 0, and 0. Alrighty. So I'm going to graph it maybe here. Let me remove the erase. I need the color I can deal with. Here it is. All right, let's go back. So the first point, okay, x200 is 1. For y, 030. And for z, we have 006, 3, 4, 5, and 6. Here is 6, so this is the third point. Remember, we graphed something similar before. So you go straight down to this, then straight to this guy, and straight up. What do we have again? We have a pyramid. So this is our surface, guys. What do I need from the surface? I need R. This is R. By the way, in the Y, this is a 3, and this is 2 in the x-axis. So here is 2, and here is a 3. So what do we have? We have this right triangle. This is our region R. So now I'm going to go back and copy down. So flux is equal to the double integration of 6 minus 3x minus 2y. And we say what? dA over R. Now R can be region of type 1, type 2. Let's take it a region of type 1. So what we do in the region of type 1, we take a horizontal line, vertical line. So region of type 1. So what is this equal to? 6, double integration, of course, 6 minus 3x minus 2y, dy dx. I took it as a region of type 1, so dy dx. Okay, for the x, starts from where? Who's that? This is x equal to 0. This light is going to keep on moving, and definitely it will finish here, which is what? At 2. So for x, it's from 0 to 2. How about for y? Who's at the bottom? This is y equal to 0. What is this? This is y equal mx plus b. What's b here? It's a 3. Now this point, by the way, is 2 and 0. And this is 0 and 3. What's the slope of that? 0 minus 3 over 2 minus 0, which is minus 3/2. So what's this y equal to? Minus 3/2 x plus 3. So up to minus, we put it here, minus 3/2 x plus the 3. This is how you set up the equation. Now, what do we integrate with? We're going to integrate with the inside. So this is equal to the integration from 0 to 2. Now let's integrate with respect to y, guys. What's its integration of 6? 6y. Minus, what's the integration of that? 3xy. What's the integration of that? Y squared over 2. 2 goes with this one. So minus y squared from 0 to minus a 3 over 2x plus a 3. And then we say dx. Now what do? We replace x with this value. So this is the integration from 0 to 2. 6 times minus 3/2 x plus a 3 minus a 3x times minus a 3 over 2x plus 3 and minus a 3/2 x plus a 3 all square dx. And this is equal to the integration from 0 to 2. I multiply, I get what? This one with this one is a 3. So it's minus 9x plus 6 times the 3 is 18. Here is going to be plus 9x squared over 2 minus the 3x times this is minus 9x. Here minus, if you open that, what do you get? You get 9 over 4x squared. Then the first times the 2, the second times 2. So the first times the second is minus 9 over 2 times 2 is minus 9. X plus 9 dx. Expand that. Minus 9x plus 18 plus 9 over 2 x squared minus 9x minus 9 over 4 x squared plus 9x and then minus 9 dx. Now minus 9x plus 9x, they go away. 9 over 2 minus 9 over 4. So you can make this one actually 18 over 2 minus 9 over 18 over 4 minus 9 over 4 is 9 over 4. So this is equal to the integration from 0 to 2, 9 over 4 x squared. So I'm done with these two guys. Minus 9x, is there any x here left? Nothing. Minus 9x. 18 minus 9 is plus 9 dx. Now let's integrate. What's the integration of this one? So this is 9x squared over, it's x squared over 2, and there's 4, so over 8. Minus 9x squared over 2 plus 9x, and this is from 0 to 2. So this is going to be 9. Put the 2 here, you get 4 over 8 minus 9. Same thing here. Here there is no square, sorry. I have no idea where did this square come from. So put the 2 here, 2 over 2, plus put a 2 here, you get 18. When you put the zeros, you get zeros. So this is 9 over 2 minus 9 plus 18. So it's 9 over 2 plus 9. 9 times 2 is 18. 18 and 9 is 27 over 2. This is the flux, could be cubic square, what is this? Cubic meter per second, whatever the cubic centimeter per second, it depends how is the flux coming. It's in volume, guys. Last question. F of x, y, z is zx, zk only. So this is f. All right, so what do we say? Flux. I will always start with the formula. Over S. So let's make it over R. F dot N 1 plus Fx squared plus Fy squared, then df. I would start always with N. To start with N, let's go to Z. Okay, oriented upwards. So we're going to say what? That G of XYZ is Z minus what? F of XY. By the way, this one is F of XY. Bring it to the left, we get Z minus 5 plus X squared plus Y squared. This is G. Now the gradient of G, let's differentiate with respect to X, you get 2X. I. Differentiate with respect to Y, you get 2Y. J, differentiate with respect to Z, you get ZK. Magnitude of the gradient of G is square root of this, which is 4x squared plus 4y squared plus, this is 1, by the way, the derivative of this one is 1, plus 1, which can be written as 1 plus 4 outside, then you have x squared plus y squared. So the gradient, so n is going to be 2xi plus 2yj plus k divided by the square root of 1 plus 4 x squared plus y squared. This is n, guys. Now f dot n, f is nothing but zk. So you have 0i plus 0j plus zk. When you multiply it by this, divided by 1 plus 4 x squared plus y squared, what's going to happen? 0 with this is gone, so the I is gone. 0j is gone. So z times that is z. So what's the answer? Z divided by square root of 1 plus 4 x squared plus y squared. This is f dot n. Now let's look at this. Now what's f of xy? Remember, f of xy, it's this. It's the z, which is equal to 5 minus x squared minus y squared. If I differentiate with respect to x, we get minus 2x. When I differentiate with respect to y, we get minus 2y. So from all of this, we get that the square root, which is that one here, of 1 plus fx squared plus fy squared is nothing but the square root of 1 plus 4x squared plus 4y squared, which is equal to the square root of 1 plus 4 x squared plus y squared. What did I say a minute ago? This must match the gradient. So now what do we say, guys? So f dot n times the square root of 1 plus fx squared plus fy squared. Who should remain? Okay, where is f dot n? F dot n is this. When I multiply it by this, what's left? Double, nothing but z. It's nothing but z, which is equal to what, by the way? It's equal to 5 minus x squared plus y squared, isn't it? That's a z, which is equal to 5 minus r squared. I'm going to convert everything to r. You will see in a minute. So the flux here is double integration of the whole thing is 5 minus r squared f dot n, all of this, multiplied by what? By r dr d theta. Now over what? Over the region of. Where is my region? How does this graph look like? Cylinder and this thing. All right, let's make the graph, guys, and see how does the graph look like. This one, paraboloid, it's a paraboloid that goes to Z5. We have graphed it so many times, and it goes down. So let's graph the paraboloid, guys. And if this is the z-axis here, okay, and the y, so paraboloid, yeah. So this is root 5, by the way. Oh, let's say, no, let's not put this one yet. I'm gonna figure it in a minute. So this is our graph. All right, and this is between x and y. You go to the here. Okay, remember if you take, where am I? This one here, if you take x to be 0, y will be root 5, right? And if you take x and y, z is 0, you get actually x squared plus y squared equal to 5, which is circle of radius root 5. So I'm going to make my circle of radius root 5. Here it is. So I don't need all the way down. I don't need to go all the way down. And this is the same thing here. So this is root 5, root 5, root 5 negative. How did I get this one, by the way? I went here. Where am I? This is our Z. This is what I'm trying to graph, right? So you have Z equal 5 minus x squared minus y squared. First, you let Z equal to 0. So what do we get? We get x squared plus y squared equal to 5, isn't it? This is a circle of radius root 5. Here it is. So this is, I graphed it in the xy plane. All right. Now, what's the other one? It's a cylinder, x squared plus y squared equal to 4. Let's graph the cylinder. This one, now x squared plus y squared equal to 4. This is a circle of radius what? 2. Here is 2, guys. This is a circle of radius 2. So this is 2 and negative 2. This circle is going to go up to create what? A cylinder. So the result here is the following. We will have this like kind of dome here on the top. And this is the surface that we're talking about. This surface, where is the base? This is our base R. What kind of base here? This is a circle of radius what? 2. So this is our base. Circle of radius 2. So how do I continue here? So this is equal to the 5 minus r squared times r dr d theta. Now, if I take r here, this is our r, starts from 0 to 2 as usual. And to finish the whole circle, it's full rotation from 0 to 2 pi. Now, this is equal to integration from 0 to 2 pi. Now, remember, we start the integration from inside. Open this. So this is the integration from 0 to 2 of 5r minus r cubed. I'm multiplying this r by 5 and r by this, dr d theta. Now integrate. So this is the integration from 0 to 2 pi. The integration of 5r is 5r squared over 2 minus the integration of this one is r4 over 4. And this is from 0 to 2 d theta. Put the 2, guys, what do you get? The integration from 0 to 2 pi. If I replace this with 2, we get 4. 4 over 2 is 2. 2 times 5 is 10 minus. If I put the 2 here, 2 to the 4 is 16. 16 over 4 is 4. 10 minus 4 is 6, goes out, and now you have the integration from 0 to 2 pi of d theta. But we know that always this is 2 pi, so the answer is 12 pi, because this one is 2 pi. This is, guys, the surface area. Oh, sorry, this is exactly the flux of water that's coming out of this space. Okay, I hope you guys enjoyed it. This is the last one. And so what do we have today? Today we learned of mainly the flux, surface area of a surface, and the flux out of the surface. That's it. We see you in the next section, which is 9:14. You guys have a good day.